the string thing and not drawing on it and put it down.
Oh, are we ready? Alright, get up over there. Alright, now I gotta go try to come from the top here.
No, that won't be hard as me.
Yeah, okay, so we come over this way. Okay, well, we were close. Can you lift this finger?
Which one?
Your middle finger. There, and now it meets a little bit better. Okay, good enough for government work, as they say. So basically, theoretically, this right here, and then focus. Focus. Focus, Dino-san. And where our little push pins were are the two foci, called F1, F2, just to make the difference. And somewhere right here in the middle is the center. And the idea is the length of the string is for each point on here, let's call this x, y, the distance between, well, let's do a couple of colors.
Purple.
Purple and green. Okay, so if we do the distance from this point to this focus, and the distance from this same point to that focus, the idea is that wherever we are on the ellipse, the sum of the distance to the two foci will remain constant, which is another way of saying is this length of the string is the same length of the string. F1 plus F2, or the distance between x, y, and F1 and F2 is the length of the string, and this stays constant. So, what would that... that's the idea. And go ahead and pause color. And orange, we actually need two more colors. Okay, so here's our ellipse. Now the major axis is running which way? Horizontal or vertical?
Yeah, very good idea.
Horizontal? Excellent. Yes, the major axis is running horizontal. Major axis. I'll put that inside. Major axis and the minor axis. Is it pretty self-explanatory or self-evident, I should say, as to why this one is called the major axis and this one's called the minor axis?
Yes.
Oh, good. Just checking. All right. So, a couple other measurements for an ellipse. The distance from the center to the vertex along the major axis is, we call that distance A. And so since this is the center, it's the same distance to, oh, you get the idea, to A. So we have a vertex over here and a vertex over here. And the distance between, so the length of the major axis is 2A, because A is the distance from the vertex to the center. Now going the other way, along the minor axis, from the edge to the center, we call that distance B. And another B here. So the minor axis length is 2B, and in blue, the major axis length is 2A. And I know what you're all thinking. You're thinking, so what is the standard form for the equation of an ellipse?
Yes,
I knew it. So there's two versions of it, because depending on whether the minor axis is this way or this way, we have a slightly different version. So for this one here, and during our commercial break, Caleb asked a very good question. As the foci get closer and closer together, there will be less and less of a squishing or stretching of the ellipse. And so the closer they get, the more the ellipse is going to look like a circle. And if they finally actually get to the circle, well then the distance from any point to one focus is going to be equal to the other focus, because both foci will be in the middle, and then you have a radius. Okay, so for this type of an ellipse, the equation looks like this. And I screwed up already. What a great blank stare deer in the head.
We'll be getting this for a while.
Oh, I'm sure I will. And yeah, so that's that. So what do you think the, let's see, brown or black? Black. Oh, at least you agree. So then the other form, for one that goes this way, is, which way did they write it? And, yeah. They still have, it still looks like this. But A is large, since A is the distance along the major axis, if it goes this way, the major axis is running vertically the same way that the y-axis is, so we need to put A under the y-axis and B under the x-axis. And by the way, just to pursue the idea of ellipse versus circle, let's take this equation here. And let's say that A equals B. And let's call it R. What's going to happen? These two have a common denominator, so I can combine them into one term. And then if I multiply both sides by R squared, cancel, and we have x squared plus y squared equals r squared, which is the equation of a circle. Pretty exciting, huh? So that shows you the relationship between an ellipse and a circle. You don't have to know that, but it's just interesting. Well, to me. But then again, I'm a math nerd, so that's okay. So yeah. So for starters here, we're going to talk about ellipses that have the center at the origin, 0, 0. So we're going to start with small. Later, this will look a little more complicated, but this gives you the idea and a good place to start. So let's dive into a couple examples. 71.1, we have x squared over 25 plus y squared over 9 equals 1. Now, based on what I've told you here, that if the major axis is 2a minus 2b, a is always greater than b. Looking at this, is this type of an ellipse or this type of an ellipse? Major axis goes which way? Vertically? Horizontally? You care? Sideways? Squareways?
Go for it.
Downways.
Yeah. The larger number is under the x term,
Oh,
so
that's right.
it goes this way. So I can rewrite it, if I want to put it in standard form, I would rewrite this like this. And what this tells me is that if this is the origin, this vertex over here is how far away from the center? 5. So this is would be 5, 0. The coordinates of this vertex would be -5, 0. What's the coordinates here?
That'd be 3.
0, -3, and up here would be
0,
0, +3. What did it ask for, by the way? Graph it. Okay, it's not just, yeah, if this is 5, this is not 3, but point is, that's roughly what it looks like. Yeah. Sometimes what we have to do in example 71.2 is we've got 5x squared plus 2y squared equals 15. Sometimes what we have to start doing is, it has to be in this form here. X squared over some number squared plus y squared over some 1. This has to be a 1. Which means that if we have this not a 1, we have to divide everything by whatever that number is. So we have 1 over here equals, it has to be y squared by itself up there, and x squared by itself here. So if I've got 5x squared over 15, I need to put these numbers into one number and stick it down here. 5 over 15 this way, if I need that on the bottom, I flip it to 15 over 5, which reduces to 3. 2 over 15, these come to the bottom, so I'm going to flip it to 15 over 2, which doesn't reduce. And since I need to write it in this form, what I would have to say is the square root of 3 squared, and the square root of 15 over 2 squared, and now I have the equation in standard form. And in a case like this, what you would do to sketch the graph is find A and B on your calculators to the nearest decimal and sketch it that way. We're not looking for incredibly accurate sketches, but it does have to give the idea. Oh, now that we have it, you can't really tell in this form as to which one is greater. Actually, this one, well, I'll tell you, this one's greater. So that tells us that since the larger term is under the y squared, that it's going to be an ellipse with a vertical major axis.